All right, what up, fam? Let's hop right into this test review video on sampling distributions. So here we go. We're going to read every question. According to DuPont Global Automotive Color Popularity Report, 23% of all cars manufactured in the current year are white. So the key words here are going to be all. Like basically all these questions that are going to be of this nature, and this is going to be true for a lot of these questions. There are going to be two categories to think about. There's going to be parameters and they're going to be statistics. Basically, the statistics will estimate the parameters. So the parameters here are the true values, whereas the statistics are some kind of calculated or estimated. So calculated slash estimated. I say estimated because it's from a sample, so it's not like you're guessing what that is. You're going to be calculating something from a sample to estimate the parameter. Parameters are the true value for populations, and the statistics are for samples. In general, the symbols that we are going to use for parameter are going to be the Greek letter mu. We are also going to use the standard deviation symbol like that, and we will also use the letter P for proportion, whereas the statistics will typically use the letter X with a bar over it for the average. We'll use an S with an X for a standard deviation, and then we are going to use a P with a hat on top to make sure it's part of a sample. So that's going to be a brief overview of what these things are. So when it says 23% of all, so this is like the word all here, and this is like only a part. So the 23% is the parameter. And this is a random sample, blah, 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 reveals that 19% were white. So the random sample giving the 19 is going to be our statistic. So we have 19 as the statistic, 23% is the parameter. That is letter B for our correct answer. Let's move on to number 2. So a particular family consists of 5 individuals. The ages of the family members are 2, 4, 6, 30, and 32. Suppose you select a random sample of 2 family members and calculate the sample minimum age. I will warn you on the actual test, the every single thing in the entire question is going to be exactly the same for this problem, except the word minimum age is going to be changed into something else. I actually forgot what that something else is, and at this point in time, it might be like a maximum, might be a range, might be an average or something. But the whole problem is the same, except this is, I don't know what it is. It's gonna be something different on the test. So don't be tricked and like circle the same exact one on the test, because it's gonna be a different one. Anyways, which of the following shows the sampling distribution? So the sampling distribution is distribution of all possible samples. That's what this means. All possible. In many real world problems, this is not possible. It is not possible to get a sampling distribution and like write them all out if you have a sample size of 3,000 and you're calculating a proportion or something. It's just, there are way too many things to write down. You might be able to get a computer to simulate it, or get a computer to plot down every single possible combination. However, when the numbers are small, when it's only 5 individuals here and you're only having a sample of 2, and in this case the order doesn't matter. By the way, if you wanted to be smart about that how many different possible things would be writing down would be 5C2, 5 things, choose 2, order not important. Just in case you wanted to remember that from previous chapter. So I apologize about my handwriting. I will work on it for the rest of this page. So 5 things, choose 2, order not important. That's what this is. Turns out this is equal to 10, and that's why this problem is short enough. All these are supposed to have 10 dots. So if they have more than 10 dots, the problem is definitely wrong. So like this letter E over here is nonsense because there's way more than 10 dots written down here. So like we kind of know this is not correct, for instance. But either way, let's write down every single one of these and calculate the sample minimum so we can figure out what our distribution is going to look like. So you're doing a random sample of 2 family members. So I could get the 2-year-old and the 4-year-old. I could get the 2-year-old and the 6-year-old. I could get the 2-year-old and the 30-year-old, and I can get the 2-year-old and the 32-year-old. If you notice, I'm starting with the 2 and then going up. Now I'm going to start with the 4 and then go up. So I could have 4 and the 6-year-old, the 4 and the 30-year-old, the 4 and the 32-year-old. So that's all those. If you notice, I have 3 of them because I didn't do 4 with the 2 because I already had that when I wrote this one down. So in the next column, I'm going to have even one less. So I'm going to have 6 and the 30, the 6 and the 32, and then the very last one in our sample will be 30 and 32, and we'll have the 10 that we expected to get. So now we're going to calculate the sample minimum. The sample minimum from all of these is 2. The sample minimum from all of these is 4. The sample minimum from all of these is 6. And the sample minimum from this one is 30. So we want to figure out which one of these dot plots here has 4 dots at 2, 3 dots at 4, 2 dots at 6, and 1 dot at 30. The only one that is reasonable is letter B. So we got the 2, the 4, the 6, and the 1 dot all the way at 30. And again, because you're calculating the sample minimum. All right, so let's go ahead and go on to number 3. So we have this longer question. I will say these longer ones do appear intimidating, but they're not that bad once you read it. So let's read the entire thing. An Alaskan transportation company claims to keep its box trucks warmed to 20 degrees Celsius in order to keep products from freezing during transport. The dot plot below shows results of taking 30 simple random samples of 10 temperature readings from a normal population with the average of 20 and a standard deviation of 4. So this is, in other words, a dot plot is not the actual situation. Suppose 10 box trucks were randomly selected and the temperatures were measured. The sample minimum of the 10 trucks was 6 degrees. So they're claiming that it's at least 20 degrees normally, but the 10 that we selected, we got 6 degrees. So it's going to be running a little cold. You know, they're in Alaska. Is there convincing evidence that the minimum temperature is less than 20 degrees Celsius? So basically, these 10 trucks, 6 degrees is the true value. The company is telling us that no, the true value is actually 20. Is their claim reasonable based upon this dot plot with a normal population, standard deviation of average 20, standard deviation 4? Going back to the beginning of the year, just to remember that we have the plus or 1 minus rule for a normal distribution. So just like to remind us what we're talking about here, if I had plus or minus 1 standard deviation here, that's going to be 68% roughly of my population. Plus or minus 2 standard deviations is going to be 95%. Plus or minus 3 standard deviations is going to be 99.7% of the population will fall within plus or minus 3 standard deviations. So so in here, if I did that and I had this 20 and the 4, 3 standard deviations would be 3 times 4, which is 12. So that would be 8 to 32. I subtracted 12 and added 12. That would be 8 to 32 is kind of where 99.7% of the population comes from. So the idea of getting even anything outside of this is strange, but we did get one. We got one little dot at 6 over here on the actual answer. But for this actual truck problem, is it reasonable to believe that the number is actually 20 when we got 6 on our sample, given that the simple random sample only had 1 6 in the entire thing? Obviously, this company's lying. So which one of these does it say is lying? So the no's and the we cannot draw, those are all nonsense. So only the yeses have a possibility. Let's read this one. Yes, 6 is less than 20. Okay, that's nonsense. All right, we can reject the claim made by the company. It would be very surprising to get a sample minimum of 6. Yeah, that's exactly what we were just talking about for this question. Let's check out the next one. Same exact kind of idea. A doctor claims that women that are less than 5 feet tall tend to live at least 100 years old. The dot plot below shows the results of the average lifespan of 150 simple random samples of size n equals 10 women that are under 5 feet tall, selected from government issued death certificates. Is there convincing evidence that the mean lifespan of women less than 5 feet tall is at least 100? So right away, I mean, this is obviously a nonsense claim. There's no way that every single person or woman who's under 5 foot tall lives to be over 100. This is total nonsense. But how do we give the convincing evidence based upon this dot plot here? So here, this is the actual random sample of people here. So this one up here was simulated, right? This is a simulated simple random sample. This was a simple random sample from a real population. So the real population, we want to know where 100 is. So 100 is going to be looks to be like right here. Looks to be about 100. So it looks like there's 6 above 100 and the rest are not. So we have basically right away we know that not all the women are living to be over 100. The average is clearly somewhere in the 70s to 80s, somewhere in the middle over here. Let's read their answers are. Yes is 100. It's a plausible place on the dot plot. No, just because one person lives to 100 doesn't mean that all of them live to 100. This is nonsense. All right, no, a sample mean of 100 is not unusual. No, it is unusual. Look at this. No way. All right, yes, 100 is not realistic due to advances in modern medicine. I mean, maybe the teenagers who are alive today, they're all going to live to be over 100 based on modern medicine. I don't know if that's going to happen. One can hope. You never know. How this one? No, no conclusion, so it's got to be letter D, but let's read it at least. No, only 4% show an average lifespan of at least 100 years. That's what I was talking about there. We had the 6 over 150, the 150 from the original question, the 6 dots that we counted there. So we don't have enough evidence to conclude that women less than 5 feet tall tend to have an average lifespan of at least 100. So, yeah, and remember, these are all averages of size 10, but either way, clearly, no, it's a very unusual event to show up. Number 5. So each one of these questions, 5, 6, and 7, deals with the keywords here. The words are going to be bias, variability, and kind of good estimator. So the word bias here, just so we can do this kind of one by one, because they're all going to have exactly the same dots, A, B, and C. You can see the exact same dots here. This next one's about variability. But bias is talking about incorrect in the same direction over and over. Incorrect in same direction over and over. So statistic A, for instance, is wrong all over the place because it's all the way over here to the left, it's all the way to the right. It's just not very accurate whatsoever, but it's not biased because it doesn't go to the left more often than it goes to the right. Same with letter B. It's also not biased. It doesn't go really to the left or the right more at all. I mean, there's literally only a single dot above on the left there. Whereas statistic C is right more often than either of the other two, but it's to the right of it is where it's off most often. So because it's off to the right most often, it will have the largest bias by a significant margin. So the next one here, the word lowest variability. Variability is one of the words from way earlier in the chapter. This is our spread that we're talking about, how spread out it is it? I think it's extraordinarily clear that A has the largest spread. However, both B and C have a similar kind of spread that they're going about here. They only have a few dots on the edges, and most of the dots are right here. A few dots on the edges, most of the dots are right here. So statistic C might be wrong more often, or might have the correct value, but it's biased. But it's not variable. It's not getting all the values way over here. It's not getting the values all the way over here. It is pretty dang consistent where it's going. So both B and C are going to have similar variability, whereas A is going to be all over the place. So because we've talked about those things, about the bias and the variability, that's going to lead us into question number 7, whereas question number 7 is which one of these is actually the one that we would like to use. I think it's very, very clear that statistic B is the one that we would like to use because it's not as spread out as letter A. It's not biased like letter C. So letter B is the one that we're going to want to use. Here we go. Question number 8. So if we took the simple random sample of 1,700 people from California, population 34 million, and a simple random sample of 1,000 people from Detroit, a population 1 million, which sampling distribution would have the smaller standard deviation? So for this problem, we're going to introduce our very first formula that we're going to be using quite a bit. So you might want to refer back to that formula over and over, maybe write it nice big somewhere on the front of your page. I'm going to write it right here, but anytime that you are doing a very basic distribution for a proportion, every single time you'll have this formula, the standard deviation for a sampling distribution of a sample proportion, written this way. The standard deviation of p hat is going to be, we have p multiplied by 1 minus p divided by n. Please note that we have a p hat on this one. We do not have a p hat on these. The only time the p hat will show up under the square root like this is when we are doing confidence intervals later. All the other times when we're doing sampling distributions or hypothesis testing, it's going to be this p. After the other type of formula that we're often going to be using is the standard deviation of x bar. So this one over here is for a proportion when you're doing like a yes or no answer, like for instance, if you're doing votes, who's voting, voting left or voting right for your presidential election. Whereas over here would be something like average heights or average amount of money made or something like that. And that's just going to be the original standard deviation divided by the square root of the sample size. However, in order to answer this question, what we need to understand is that both of them divide by n. No matter what, your sampling distribution standard deviation divides by n. So maybe just write that down somewhere. So sampling distribution standard deviation divide by the square root of n every single time. So this one has the square root of n on the bottom, but there's a square root on the top too, which is why it's in both places. And on this one, we have the square root of n only on the bottom. Because we are dividing by the square root of the sample size, in order to have a smaller standard deviation, you need to have a larger sample size. So that's another thing. Maybe we can write that down. Smaller standard dev goes to larger sample size. And the vice versa is true, and the other way, like the other way around is true. If you have a larger sample size, you have a smaller standard deviation. If you have a smaller sample size, you'll get a larger standard deviation. They are inversely related. As one goes up, the other goes down. So for this question here, if you wanted to make sure which of these would have the smaller standard deviation, it's whichever one has the larger sample size. Please note, we never ever talked about the population size. It is absolutely not relevant. Like, we don't need to know this at all. We don't need to know this at all. This is useless information. This is useless. We don't care about the 1,000 out of a million. Doesn't matter. Detroit, smaller population size, also nonsense. We only care about the sample. California, because the sample size is larger. Boom. That is exactly what we want. The larger sample size will give you the smaller standard deviation. We're done. Moving on to number 9. So we have almost exactly the same type of question if you notice going on here. We have, suppose Texas, 26 million, Wyoming, 526,000, purchase item online. We would like to select samples from each state in such a way that sampling distribution have roughly equal variances. So roughly equal variances, roughly equal spread, roughly equal standard deviation. That means they have the same sample size. So which one of these has same sample size? Does letter A? No. Does letter B? No. Variances will be nearly the same if we sample the same percentage. No. Same sample size. The variances of the sampling distribution will be nearly the same if we have a sample percentage to compensate. That's nonsense. The variances will be nearly the same if we sample the same number. Sample size the same. Letter E. Yes. Easy peasy. Moving on to question number 10. Let's do it. All right. So number 10, we are going to our formulas. We already briefly discussed our formula rule that for the p-hat standard deviation, just in case you forgot it already. Our standard deviation of our sampling distribution of the sample proportion is p multiplied by 1 minus p divided by the square root of n. But one thing we didn't write down earlier, because it's kind of like a freebie one, but the average of your p-hat is just equal to p. So the mean of your sampling distribution is equal to the true population value. So we're going to use just these two formulas to answer this question. About 27% get this actual one, and you're doing the assuming that this is the parameter. So this is the true value, or in other words, because it says parameter 27%, that means p is equal to 27%, which is 0.27. And now it wants to know if you select a simple random sample of 25 Americans and let p-hat equals the population proportion sample, who get 30 minutes of exercise at least 5 days a week, what are the values of these two things? So we just wrote down that the average is equal to p. Well, if p is equal to 27, that means that both A and B are wrong. It must be this 0.27, one of these ones. And then For the actual formula, we just got to throw it in right into the formula there. So our standard deviation of p hat is going to be our big, huge square root of 0.27 multiplied by 1 minus 0.27 divided by, looks like 25 is our sample size. That's our n, by the way. All right. Oh, you can't even see that. I just wrote the word n, or letter n. When you're doing these on the AP test, by the way, they actually don't write 1 minus 0.27 here. They just write like 0.73. So they'll actually do the subtraction. So I am going to write that just to remind ourselves that's what we're doing. So 1 minus 0.27. There's that 0.73 I was talking about. So this is how it shows up on the AP exams like this. So I do think it's important just to note that. I've been using this in class because I think it's a little bit easier to work with. Regardless, alpha y equals enter to get that fraction going. And I already screwed up because you're supposed to do a square root first. So square root first and then alpha y equals enter. And then we have 0.27 multiplied by 1 minus 0.27. And again, you could have used 0.73 there. All over 25. And it turns out we get 0.0887. So approximately 0.08879, which appears to be letter D. Boom, boom, boom. Number 11, suppose you are going to roll a fair 10-sided die 50 times and record p hat of all the proportions at the time the roll is 3 or lower. So that means what proportion of the time is it 3 or lower? Well, the chance of it being 3 or lower, just our regular old probability, is going to be, it has to be a 1, a 2, or a 3. So 3 or lower here is going to be a 1, a 2, or a 3, and it's a 10-sided die. So our probability is going to be 3 over 10, which it seems that they are changing to be 0.3. In addition, another thing about this question I forgot to mention, it says sampling distribution p hat. We can immediately cross off A and B, and that is because our p hat, by definition, no matter what, maybe I can do this in a different color, but p hat, no matter what, must be between 0 and 1 by definition. It's a proportion of the population where something is true. So either the lowest percentage it could be is 0%, the highest it could be is 100%, from 0 to 1, guaranteed, all proportions. So A and B being 15 is nonsense right off the bat. After that, we can go ahead and use our standard deviation formula to get to the correct answer. However, by the exact same logic that I had just talked about before, if the standard deviation is 3.27, 3.24, standard deviation is the spread or how often it's wrong. So if it's wrong by 3 in either direction, that means that you have a negative percentage of people if it was 3.24. So that would have to be wrong by letter C for that reason. And then the words normal and approximately normal, it turns out this is going to be our correct formula for this problem either way. So I guess I'll just write that down. We don't actually need to go into our calculator and calculate it, because we already know what the correct answer is. We have the 50 here, we have the 0.3, we have the 1 minus 0.3, and if we did all of that work, we'd get to 0.0648. I guess I'll just do it up there anyways, just to prove that I'm not making things up. Gives you a chance to take a drink of water, relax for a moment. 0.3 times 1 minus 0.3 divided by 50, and sure enough, we get 0.0648, which is exactly what we expected because both of our answers there. But the real thing is it non-normal or approximately normal? So in order to be approximately normal for a p hat, we'll say that p hat is roughly normal if the large counts condition is met. If large counts met. What is the large counts condition? The large counts condition is very, very straightforward. It means that n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. However, when you're actually doing this, you don't actually need to check both of them. The reason why you don't need to check both of them is one of them is guaranteed to be larger than the other. They both have an n in the formula. So the real question is, what's bigger, p or 1 minus p? If p is the bigger number, you don't check it. If p is the smaller number, that's the one you check. What am I saying? Well, if p is 0.5, both of these are the same thing. But if p is like 0.3, like in our question, 1 minus p is going to be 0.7 because they're guaranteed to add to 1. you're checking to see if they are both bigger than 10, so you only need to check the smaller one. The smaller one that you're checking here is going to be the 0.3. So for the actual problem itself, we will know that 50 multiplied by the 0.3, that's going to be 15. Because it's 15, it's bigger than 10. Because it's bigger than 10, that is greater or equal to 10, check mark. It is approximately normal. Letter E. We are going to use exactly the same concept in question number 12, because in question number 12, it wants us to know we have this 27% from number 10 of getting 30 minutes of exercise. How would the sampling distribution for this of n equal 50 compared to n equal 25? And if you notice, some of them say normal or not normal, but the big thing is if I change that 50 to a 25, so if I change that 25 multiplied by, in this case, 0.27 versus the 25, but versus 50 times 0.27. So you're comparing these two things. We have n equals 50 and n equals 25. So 25 times 0.27, 50 times 0.27. This one over here is, my brain is failing me right now. What is that? 50 times 0.27 at 13.5. I don't know why that was not working in my head right now. This one is 6.75. So this one is normal. This one is not normal. So again, to be normal, the large counts condition says that these two things multiplied together must be bigger than 10. Because that's not at least 10, this is not normal. So 50 will be normal. The 25 will be not normal. Couple of these say that. The last thing to remember is what I was saying earlier. If you have a bigger sample size, you have a smaller variance, a smaller spread. So let's read through. They would be the same. No. Center and spread would be the same. No. Center would be the same. Good. The centers are always the same for these. The spread would be smaller when n equals 50. True. And both, nope, they're not both normal. The center would be the same. The spread would be smaller when n equals 50. Good. And the shape would be approximately normal only for the larger sample. Beautiful. That's exactly what we were looking for. That's our correct answer. Letter D. There we go. Here we go. Number 13. According to this poll, yet again, is the sampling of this thing approximately normal? So we kind of just practiced that right away. Over here, simple random sample was 25. We just figured out that it's not bigger than 10, so the answer is no. Don't know why I put this question on there twice. Oh, actually, I do remember now. This is the 10% condition, which is the large population condition, which is different. This one here, all this does for this check here, which we call our 10% condition, our 10% condition lets us use our standard deviation p hat formula that we have been using, the p times 1 minus p divided by n. You actually can't use that formula if the 10% condition is not met, and you have to do something different. You have to use your binomial distribution formulas. We are not going to worry about that right now. We are just going to use the 10% condition, and that's going to be fine for the AP test. Okay. So, question number 14. For question number 14, our z-scores show back up. Just in case you forgot what a z-score is, our z-score in general is going to be the value that we're interested in minus the actual average. So we'll use the word average instead of the word mean. It's not as accurate, but it's fine. Value minus average over our standard deviation. That is our formula we've been using for quite a while. The versions that we've been using, I'll write a few of them here. So we've been using, for instance, our x minus mu over our standard deviation. We have been using our x minus x bar over our standard deviation. And the one that we are going to be using for this problem is going to be our p hat minus p divided by the square root of the sample, which is your square root p times 1 minus p divided by n, just like so. Because this one right here, remember, is our standard deviation of our sampling distribution. So a couple things about it. Some people are like, well, the bar is above it on this one, but the hat's above it on this one. What's going on? As a reminder, all these on the right-hand side, these are supposed to be, this one and this one and this one are all supposed to be parameters. If possible, they're not necessarily always parameters, so that's not perfect language again, but they're supposed to be parameters. They're supposed to be values that are assumed to be true or known to be true, whereas, I don't know, I guess I'll just do red or something like that for this side, like this one, and this one here all come from samples. These are all statistics. And by the way, they call this the z-test statistic later, so technically the entire thing becomes a statistic once you've done something to it, but we're just going to leave it like that. You can call them statistics, you can call them from the sample, just to know which side you're going on, which is going to matter for us in this question, because it says right away that suppose 53% of all adults. That means that this one right here is our letter P. Because that's our letter P, it's going to be on the right hand side and it's going to be in the denominator in both different spots here. The P hat is going to be what you're doing for this part. What is the probability that less than half of the sample? So the less than part is going to tell us that we need to do a less than symbol. So right away we can cross off letters B and C and E. And then also for letters A and D, if you notice, only one of them correctly has the square root of n on the bottom, and that's going to be this one. But just note, it is possible to easily make mistakes on these, because you could see that sometimes they try to put the P value in down there instead of the P hat there. So just be careful where, I said that backwards too, but just be careful where the formulas go, because they can be quite annoying using the same letters and all that kind of stuff. Anyways, let's do question number 15. So a study of 240 randomly selected residents of a subtropical resort with 82,000 residents found that 5.4% of them exposed to this mosquito-borne virus, the dengue fever. Suppose the actual percentage of people is 3%. So P is equal to 0.03. Let P hat be this proportion. Probably P hat is more than. So we're doing probability of P hat bigger than 0.054. That's going to be equal to the probability of z being greater than, and we're going to use our formula from up above. Our formula from up above, we're using the exact same one, p hat minus p over the standard deviation. So our p hat is 0.054 minus 0.03 divided by our big huge square root, and again we're using our 0.03 value here. So we have 0.03 times 1 minus 0.03 divided by our sample of 240. But you do want to be careful you're plugging this in, because we're doing the probability of a z-score. Anytime you're doing a probability of a z-score and you're trying to figure out what this answer is, you could use the table of values that many books recommend, but I think it's much easier to use the normal CDF button on the calculator. So we're going to use our normal CDF button on our calculator here, where I'll just go ahead and write down the stuff things we'll be typing in. So we got our lower, our upper, our average, and our standard deviation. Because and visually, again, we're doing a greater than, so sometimes I think it's a good idea to put the the 0.054. 0.03 is here in the center, so 0.54 is going to be over here. It's going to look something like this. So our lower value here is going to be 0.054. Our upper value is going to be 99999. Technically, you can actually just leave it as 1 and you'll be fine. Our average is the 0.03, and our standard deviation is this ugly thing at the bottom, whatever that is, this bottom part. So our big square root, I'm just going to write square root squiggly because it's the same thing as what I just wrote here. And now we can actually do this question. So we're going to hit second vars, normal CDF. There it is. Our lower end is 0.054. Our upper is at 999. Our average 0.03. Our standard deviation, we have the square root. We have the 0.03 parentheses 1 minus 0.03, and the parentheses divide by 240, and the parentheses paste, hit it all button. We got 0.0146, and 0.0146 is letter D here. And there we go. Moving on, number 16. So if a fair coin is tossed 60 times, what is the probability that less than 1/3 of those are heads? So basically, our first thing is this question can be solved two different ways. However, the thing that we've been practicing here is n times p greater than or equal to 10. You can use the normal distribution. So if n times p is greater than or equal to 10, you can do that. So in this case, we have 60 multiplied by 1/3, and we will get 20, and that is greater than or equal to 10. Because it's greater than or equal to 10, we can use normal distribution. Use normal ... So just like we had up here, we're doing the probability of p hat being less than 1/3, which is going to be equal to the probability of z being less than, and now we have our true value 1/3 minus. Now, what is the actual population value? Well, the actual population value is really straightforward. It's 1/2. Half of them should be heads in a real world situation. So minus 1/2 divided by our square root of 1/2 times 1 minus 1/2, which is also just 1/2, divided by 60. And we're going to throw all of that in, again, using our normal CDF, same exact concept as we just did. So we're going to hit second vars, normal CDF, and we're doing less than. So because it's a less than, our lower is going to be negative 9999. Our upper is going to be our 1 divided by 3. Our average we just talked about was 1 divided by 2. And our square root here is going to be the this thing typed in. So let's do another parentheses, 1 divided by 2, new parentheses, 1 minus 1 divided by 2, which is actually a waste of time to even type in, but I just did it anyways, divided by 60, and you hit enter like this, and you get 0.0049, which is exactly what we expect. Now, I do think this is actually a bad question, and the reason why I think it's a bad question is the perfect answer is actually about 0.006, which we're going to show in just a second, because this right here, because it's a fair coin toss 60 times, this is a binomial distribution with n equals 60 and p is equal to 0.5. And anytime you're trying to do less than or equal to, you can simply use the binomial CDF button. So the probability of the number being greater or less than 20, that is less than 1/3 or that. So you have a probability of less than 20 is guaranteed to actually be our binomial CDF here. If we actually went through and we did our binomial CDF. So binomial CDF, we had 60 trials. Our p-value is 0.5. We're going up to 20. And you can see the true value, this actual number is 0.006745, which is extraordinarily close. I mean, you're off by, you know, about 0.08 of a percent. Which is almost nothing, but the true value is down here. So if you like wrote this somewhere, it's like, where the heck's the actual answer? That is the actual answer, but this is the normal approximation, which is what we've been practicing in class. Okay, let's move on to our next page here. So number 17 here, we have our ESP situation here, extrasensory perception. Professor Breedy looks at cards that are hidden from the subject. Each card contains one of 4 figures, star, circle, wave, whatever. She looks at 100 of these cards, tries to read her mind and guess the shape, so you have a 1 in 4 chance of getting it right. Which of the following is closest to the probability that the subject gets 30 correct if the subject does not have ESP and is just guessing? So basically, we've been doing questions just like this quite a bit. We know that the true population parameter in this problem is going to be 1 divided by 4, which is 0.25. We know that the sample that we're looking at here is going to be 30 correct, which is 30 over 100, which is 0.3. And we want to know the probability to get more correct. So just like we've been doing, the probability of p hat being greater than 0.3 is going to be equal to the probability of our z-score being greater than, create our z-score. Now we put the p hat first, or no, sorry, we put the p hat first, subtract the p-value, divide by the value of p. Sorry, p-value is a different thing. I shouldn't say that. The value of p, and then our 0.25 on the bottom here, 1 minus 0.25 there, and then divided by 100. And now we just got to calculate this bad boy, which we're going to be using our same exact buttons we've been doing before. Our normal CDF, we're doing a greater than, so our lower is actually that 0.3. Our upper value, I'm just going to put 1 just to prove a point here. And then our average is going to be 0.25, and our standard deviation is going to be 0.25 times 1 minus 0.25 divided by 100. And it looks like we have 0.1241, which is letter C. 0.1241. And that's pretty much it. Don't have much else to say about that question. Let's move on to number 18. So number 18 is going to be our very first question that uses our new formula that we haven't used yet. Good news is the formula is easier. The formula, just in case you forgot it, the standard deviation for a sample distribution of a sample mean is going to be simply the original standard deviation divided by the square root of the sample size. So in this particular problem, right away, I'm seeing that we have these numbers here. By the way, the reason why I knew it was this formula and not our proportion is because, first of all, the word proportion doesn't show up anywhere. Or it's not like a correct or incorrect situation, and you have these big huge numbers, and big huge numbers like that are going to be averages. It's not like every time, but usually. All right, regardless, our standard deviation is 870, and you're dividing it by the square root of 100. Square root of 100 is 10, so 870 divided by 10 is just 87. Again, feel free to use a calculator. And which of the following are true? The mean and standard deviation. The mean is identical, and the standard deviation we just calculated. Boom. Letter A. Not much else to say. The central limit theorem refers to which of the following characteristics of the sampling distribution of the sample mean? It said, just so before I even read any of them, the central limit theorem says that so long as your sample size is large enough, we typically use the number 30. So long as your sample size is large enough, the shape of the sampling distribution will be normal. So regardless of what the original shape is, as long as your sample size is large enough, the sampling distribution shape will be approximately normal. So let's read it. Regardless of the shape of the population's distribution, the sampling distribution of the sample mean from sufficiently large samples will be approximately normally distributed. Well, that's basically perfect. So I guess I can just read through all the other ones and make sure that they're wrong, or why they're wrong. Regardless of the shape, population standard distribution, standard deviation of the sampling distribution of the sample mean from sufficiently large samples will be. This is a true statement, but it's not the central limit theorem. This is the 10% condition. That's what we were checking there before. That's our 10% rule that we were talking about. Regardless of the shape of the population distribution, the mean of the sampling distribution, even if it's a small sample, the mean of all sampling distribution is identical to the mean of the original, regardless of the original shape or the size of the sample. This is true no matter what, no matter sample size. So the mean, that's why we say the mean is an unbiased estimator. As you select larger and larger samples from a normally distributed population, no, the central limit theorem says that it's approximately normal if something else happens, not that if it's from a normally distributed population. If it's from a normally distributed population, it's always approximately normal regardless. So both D and E are wrong. Like I said, letter A is just perfect. All right. Question number 20. Suppose that at Northside High, the number of hours per week that seniors spend on homework is approximately normally distributed with a mean of 18.6 and a standard deviation of 6. We repeatedly select simple random samples of 36 seniors and calculate the sample mean number of hours they spent. The shape of the standard distribution of the sample mean is, well, our sample was at least 30, and therefore the shape of the sampling distribution is approximately normal. So n greater than 30, boom, normal. That's it. We're done. So notice the difference there. The large counts condition, n times p greater than or equal to 10. That's the proportion situation, the sampling distribution, the proportion approximately normal. Whereas this one, it's n greater than 30, approximately normal. Moving on to question number 21. The question number 21, the histogram below was obtained from data on 750 high school basketball games in a regional athletic conference. It represents the number of three-point baskets made in each game. What is the range of sample sizes the researcher could select from this population without violating the conditions required of the application of this formula and the central limit theorem? So the central limit theorem, we have to have at least 30. So this part right here, at least 30. So we do have to have at least 30. So that's at least 30. That's at least 30. That's at least 30. This one is too big and is not less than 75. 50 to 75, maybe that applies to the other one, but the other one is the 10% condition, that you can't have more than 10% in your sample size. So the data was 750 high school basketball games. So we want to know what is 10% of 750 times 0.1 is going to be 75. So it's from 30 less than or equal to x less than or equal to, or n, sorry, less than or equal to 75, which is, in fact, letter C. Checking out problem number 22. So question number 22, sense of labor force, blah, 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 blah. We have a mean of 20.5 and a standard deviation of 15.4. Which of the following represent the probability of a random sample of 40 people have a mean that is greater than 25 minutes? So yet again, just a reminder, we're doing our z-score calculation because we haven't done exactly this one. For this one, remember our z-score here is going to be our actual value minus our true population mean divided by our true standard deviation. For this particular question, we are going to be using x minus the average of the sampling distribution divided by the standard of the sampling distribution. So the sampling distribution there is when you have to divide by the square root of 40 for our answer. So in this problem, the x value that we're looking at here, x is going to be equal to the 25, the 25 that we're wondering about. Our average of our sampling distribution is going to be 20.5, and our standard deviation of our sampling distribution is going to be 15.4 divided by the square root of 40. So which one is it? Well, let's just go ahead and set this up then. So we're doing our probability greater than. So z is bigger than, and we need to do x minus the value that we're interested in, 25, minus the true value, 20.5, divided by the 15.4 over the square root of 40. Woof! All right, and again, n 40 is the n value there. And we're using that same exact formula from the previous page where this was our standard deviation divided by the square root of n. Okay, looks like we have letter B. Easy peasy lemon squeezy. Let's move on to number 23. Our very last multiple choice question. Thank goodness we're almost done here. So we have a factory produces plate glass with a mean thickness of 4 and a standard deviation 1.1. Simple random sample of the 100 sheets to be measured. Sample mean thickness of 100 is computed, which is the following probability. The average thickness is less than 4.1. So exactly that same situation as the previous types of problems. We're going to jump right into that formula for it. So we're doing less than z less than 4.1 minus the true average 4 divided by our standard deviation 1.1 divided by the square root of the sample size divided by the square root of 100. And again, we have to use our calculator to do this. We're using our z formula. So normal CDF, our lower, we're doing a less than. So less than means 4.1 is the upper value, and our lower is negative 999. You could enter in 0 for this particular question because you can't have a negative thickness. Doesn't make sense to have a negative thickness. So we have our average is, what is our average? 4, and our standard deviation here is going to be 1.1, not square root yet, 1.1 divided by the square root of 100. And we get 0.818. So 0.818, which one is that? Letter A. Boom, boom, boom. We did it. All right, moving on, number 24. I'm gonna take a break. Let me take a pause. All right. We're good to go here. Let's actually finish this free response questions. Here we go. So, a large pet store that specializes in tropical fish has several thousand guppies. Okay. The store claims that the guppies have a mean length of 5 centimeters and a standard deviation of 0.5 centimeters. Maybe we should write this down early, what these things are. So we know our actual average of the population here is going to be 5 centimeters, and that is also going to be our sampling standard deviation in the event that we need it. And the actual standard deviation of the population is claiming to be 0.5. There we go. And you come to the store and buy 10 randomly selected guppies and find the mean length of your 10 guppies is 4.8 centimeters. Okay, so that means our actual sample average here is going to be 4.8. And also our standard deviation of our sampling distribution is going to be 0.5 divided by the square root of 10 because we have 10 guppies. This makes you suspect the mean length is not what the store says it is. To explore this further, you assume that the length of guppies is normally distributed and use a computer to sample, blah, blah, blah. So first of all, my own first thought is 4.8 is not really that far from 5, and with a standard deviation of 0.5, this is actually completely reasonable. So I kind of do believe the store right now, but we'll see what this dude says. Here's your dot plot of 200 samples. So this is an estimation or a simulation of a sampling distribution. So this is not the full standard sampling distribution, because the full sampling distribution of 10 guppies from several thousand guppies would be, just to give an example, let's say it was 3,000 guppies. Then it'd be 3,000 times 29999 times 2998 times 2997 times 2996, and then divided by 5 factorial, which is 120. So times 10 to the 15th power, we're talking in the trillions there. I think that is trillions, right? 15,000. Yeah, 2 trillion dots if you wanted to actually put all of them on here. We put 200 of them. That's good enough. All right. Either way, we put our 200 here. Let's actually read these questions now. What is the population in the situation? And what are look at this. We already did it. We've already did all of our population parameters. Here are our population parameters right there. Boom. There's our population parameters. And the population in question here is the several thousand guppies. So I guess I'll write this all the way out. Nice and neat. Let's do that. Let's do our nice and neat answer. So population is the several thousand guppies. At this store. Okay, there's our population, and we have been told that, I already wrote them down. These are the same ones, so I'll just write them again. Our actual average for this problem is 5, and our standard deviation is 0.5. Okay. The distribution of one sample. What have we been given about the sample? The sample is n is equal to 10 for our sample size. The average of the sample was 4.8, and we actually don't know the standard deviation of it, but it also doesn't matter. That is the only information you've been given about the sample, I think. It was randomly selected. I guess you could add in randomly selected. Randomly selected. Probably could be good to include that. Is the dot plot above a sampling distribution? I just said no. It is a simulation one. You can't actually put all the trillions of dots on there. It is a simulation of one. Okay. And letter D. Do you think the story... look at this. I already answered that question. Do you think the story is being honest? Yeah, sure. And I guess they want to use the dot plot idea. So how many of the dot plots came up to be about 4.8? Plenty of the dots showed up in this section of being 4.8. Sure, 4.8 is reasonable based upon the dot plot. Reasonable for an average of 10 based on the dot plot. Now, if it was an average of 4.6, probably not believing you anymore. 4.7, I'm on the edge here, and actually we're going to learn a statistical method later in the year that's a more solid than just, seems good enough to me. Just because I haven't actually checked these answers, I do want to see what their answers are. Because this is all, from a computer-generated test here. I didn't actually check all my multiple choice. I'm going to do that right now, make sure I didn't screw up. All right, good news. I checked them all. We did get 100% multiple choice. We're doing good. Let's read their answer choices, comparing and contrasting to mine here. So, letter A, the population is all the guppies at the pet store. Okay, good. Given the population mu is 5, standard deviation 0.5. We did beautiful here. They used a few more words, I think. my few words is fine. Okay, sample mean is 4.8. Beautiful. Sample size is 10. Beautiful. Randomly selected. I think my answer is better because I answered randomly selected. I'm giving them a P on this one. Letter C, no, it is not. It's a simulation of one. This is an approximation by only having 200. All possibles, many more than 200 values. There's trillions of values, like we said before. Good enough answer. It's a simulation. And because 21 were 4.8 or less, it would not be that surprising. We do not have convincing evidence. Sure, 4.8 is reasonable. Yeah, their answer is kind of more perfect, but I mean, it's reasonable based on the dot plot. Easy enough. I'm moving on. We're going on to question number 25. Let's do it. I don't want to throw that answer key away. I need that for later, just to double check my answers against theirs on this number 25. The figure below shows approximate sampling distribution of 4 different statistics intended to estimate the same parameter. The true value is 42. So the true value is like right here. I'm going to go ahead and kind of mark it on all of them. Among the 4 statistics, which 2 statistics have the smallest bias? So remember from the previous one that we had talked about bias. Bias is incorrect in the same direction over and over. So on this one, there's not very much bias. It seems to be smack dab in the center. Letter B, also not biased. It looks to be all over the place. But letters C and D are both biased because we have a bunch of things off to the right. So we'd call statistic C a right bias, and statistic D is going to be left biased over here. So how are we going to write this answer? I would say C and D are incorrect in the same direction over and over. C is right biased and D is left biased. Whereas A and B are unbiased. Poof. C and D. So which have the smallest bias? So A and B have smallest bias. Okay, good enough. Letter B. Of the 4, which has the smallest variability. So remember, this variability is going to be spread all the way out. So I guess I'll just do this red color for the spread. If you notice, A is pretty compact here. It's between like 25 to 60 and kind of clumped up. Letter C here is between like 35 to 70. It's even more clumped up. So C has even less variability than A, whereas B is all over the place. B is just all the way over here, all the way over here. It's got bars going up on both sides. It's all over the place. Letter D is actually not too bad. It's a little bit more spread out than the others, but at least it's, symmetric and, somewhat, getting more values towards the center, whereas this one's got the highest variability. So in terms of variability, I would say we have the lowest, still pretty low, medium variability, and then high variability. And remember that variability does not care about bias. It only talks about how often you're getting the same values over and over again. So like this letter D down here might be a biased one where it's always getting off to the left, but it's getting off to the left in a consistent fashion. Whereas letter D is wrong, left, and right all over the place. So which has the smallest variability? In my opinion, it's quite clear for the reasons I just said, that A and C have the smallest variability. So I guess we could write that down. We would say that A and C are clumped together, and thus we have lower variability than B and D. And from this information, the idea is A and B are the low, A and C are the low variability questions, whereas A and B are the unbiased ones, and therefore A is the better choice. A is best due to combination of low bias and low variability. Okay, let's read our answers here. I just said not to throw it away. Here we go. There's my answers. Here's their answers. Statistics A and B have the smallest bias. Center of the histograms are closer to 42, while the histograms for C and D are centered over a number further away from 42. So it's incorrect in the same direction over and over again. Letter B. So we're good enough there. A and C have the lowest variability because values tend to be closer to the center. Good enough. And A has low bias and low variability. That's literally exactly what we said. All right, beautiful. We're doing 100% on that. FRQ, both me and the book are in agreement. Let's do question number 26. So, question 26, power companies severely trim trees growing near their lines to avoid power failures due to falling limbs and storms. Applying a chemical to slow the growth of trees is cheaper than trimming, but the chemical kills some of the trees. Suppose that one such chemical would kill 20% of sycamore trees. I gotta pause. I had to get my water because Red Bull is not hydrating, you know. We need some real hydration here. All right. Number 26, power companies severely trim trees growing near their lines to avoid power failures, blah, blah, blah. We already talked about that. Suppose that one such chemical would kill 20% of sycamore trees. The power company tests the chemical on 250 sycamores, and I know we need to write on top of something, so I'm going to. Okay, power company tests the 250 sycamores. Consider these a simple random sample from the population of all sycamore trees. So one does kill 20%. So for letter A, we already know, calculate the mean and standard deviation. We already know our formula from before. The mean of our sampling distribution is equal to P is equal to the true population value of 20%. We will simplify it to 0.2. If it makes you happy, you can write 0.20. And the standard deviation of our sampling distribution, we already know that formula. We've written it so many times. P times 1 minus P divided by the square root of n, going to be over here our square root of 0.2 multiplied by 1 minus 0.2 divided by 250 sycamore trees here. And I guess I should change that to an approximate value. And actually getting this number here, we have second square root alpha y equals enter 0.2 multiplied by 1 minus 0.2 divided by 250. And we're going to have 0.0253 as our approximate answer there. Beautiful. And that's it. In letter B, calculate the probability at least 20% of the trees in the sample are killed. So at least 24, bigger than 24. So the probability of P hat being greater than 0.24 going to be equal to probability of our z-score being greater than that same 0.24 minus our 0.2 divided by our big huge square root of 0.2 times 1 minus 0.2 divided by 250 approximately. And don't forget, in case you had watched it from a previous part of the video, this right here, what that's coming from there is our P hat minus P divided, and our z-score here is going to be equal to the square root of P times 1 minus P divided by n. Easy enough. And yeah, we just got to calculate this. We're going to use our normal CDF button for this in the calculator. So we have our second var's normal CDF. Greater than situation means our lower is 0.24. Our upper is going to be 999, but again, you can just leave it as a 1 if you want to. Our average in this situation, we already wrote down, was exactly equal to 0.2, and our standard deviation is this thing that we're typing in. So we have a second square root, and we have 0.2 times 1 minus 0.2 divided by 250. And you paste it, and you hit enter, and you get approximately 0.056 as our two answers here. So there, and I guess this is part of the answer. That's part of the answer, and then this is the answer we're looking for. Let's check out the answer keys version of this one. So over here, they said that we had the 0.2, 250 less. Ooh, they checked our 250 less than 10% of all sycamore trees. I didn't check my standard deviation formula. I don't think I will be taking off for that. Also, it didn't. I just used my normal distribution approximation right away. I didn't check my n times p. I'm probably getting a p on the actual test. If this was like a test question on the actual AP exam, I would have not have gotten full points because I didn't check my 10% condition or my large counts condition to get the full credit. Our calculation was right though. Using technology, we got the 0.0548. That's exactly what we did. We got 0.0569. I wonder why. What did we do? Do we do anything different? 0.0025. I think mine is just more of a perfect answer than theirs. Yeah, they use 1.6. Yeah. Mine's better. This is correct. 0.0548 is fine, but theirs has rounded values. Like if we went back to the square root button just to show you guys that I'm not like making things up. So in case I had like 0.2 times 1 minus 0.2 and then divided by the 250, if you notice they have 0.02529, so they're using the 0.25. Like if I go back up to this one and I just delete this entire square root and type in what they said, which is 0.25, now I'm going to get that. Well, of course I didn't. Let's 0.025, right? That's the problem. 0.25. So there's their 0.548 that they're getting. I think their answer is actually wrong. It's been rounded. So I'm going to go ahead and give them partial credit. So I lost points because I didn't check my large counts condition, but they lost points because they did not use, they used rounded values throughout the problem instead of exact values. Truth be told, my error was bigger than their error because with the work that they showed, the AP test would probably give them credit for it because of the work they showed. Whatever. Either way, I'm fine with it. Let's move on with our lives. Number 27, the service department of large automobile dealership keeps records of the odometer readings of cars that it repairs and determines that the distribution of miles driven per year by all of its customers has a mean of 14,000 and a standard deviation of 4,000. So distribution is skewed to the right. Suppose a random sample of 12 cars is selected from the hundreds of cars they have records, and the mean number of miles per year is calculated. What is the mean of the sampling distribution? The mean of the sampling distribution, regardless of the original shape, is always equal to the mean of the original. So because the mean of the original are average of, I don't know why I wrote that. The average of the sampling distribution is equal to the actual average, which is equal to 14,000 miles. If you want to write the miles, you can. Is it possible to calculate the standard deviation of X bar? So you can only calculate the standard deviation of X bar if it is true that you have selected less than 10% of the population. So is 12 less than 10% of population? Yes, 12 times 10 is 120, and the question says thousands somewhere, hundreds of cars. So it has hundreds, much less than hundreds. And therefore, we can calculate our standard deviation of the sampling distribution. Our standard deviation of our sampling distribution is the original standard deviation. The original standard deviation is 4,000, and you're dividing by the square root of the sample size, which is the square root of 12. Approximate answer here, we're going to have 4,000, and we are dividing it by square root of 12. And that's going to be 1154.7. 001. Right, easy enough. Letter C. Describe the shape of the sampling distribution of all cars. So because the n is not greater than 30, it is absolutely not normal. Instead, it is probably going to be the same exact as the original. So since N is less than or equal to 30, because N is actually 12. The sampling distribution will take a similar right skew shape, but less skewed. The skew will not be nearly as bad as it was before, but it will still be skewed because our N is not greater than or equal to 30. That should be our last question. Let's double check our answers. So our average is 14,000 miles. Perfect. The 12 is less than 10% of the entire population. We have the exact calculation. Because N is less than 30, sampling would be skewed to the right, but not quite, but less skewed. 100% for both of us. Love you guys. Peace out. Have a great rest of your day. Good luck on the test. Why is this not stopping?